example 4b, we need to compute the exact value of the tangent of 2 times the arcsine of 2/5. Per the order of operations, we are going to begin inside the parentheses. So you do see an arcsine here, so we are taking the arcsine of 2/5. However, this arcsine is being multiplied by 2. Okay, so you cannot ignore this 2 that I've highlighted in yellow. Okay, let's concentrate on the arcsine of 2/5, and then we will return to the original problem. So we know that arcsine, or any of these trig inverse functions, you plug in a number and you're going to get an angle as the output. Okay, so we're going to let theta be the arcsine of 2/5. Okay, because arcsine of 2/5 is just some angle. Okay, so we're going to call it theta. Okay, so what does this mean? If we take the sine of both sides, okay, we will get that the sine and the arcsine will cancel. Okay, so let me write this out for you. Okay, so the sine and the sine inverse will cancel here. We're going to get that the sine of theta has to be 2/5. Okay, so if we look at that, okay, and we also need to keep in mind the domain and the range of arcsine. Okay, so domain, if you flip back to page 7, you can plug in any number between -1 and +1. 2/5 fits that bill. Okay, so that's a perfect input. The range, the sort of output that is going to be returned, the sort of angle, the range of arcsine is -π/2 to +π/2. Okay, so basically, if we write this out, arcsine of 2/5 is the angle theta in the range from -π/2 to π/2, whose sine is 2/5. Okay, so we know with arcsine, we need to be looking at the right-hand side of the unit circle. Okay, so again, if I just erase some of this previous stuff, we are looking for the sine inverse of 2/5. We're looking in quadrants 1 and 4. Okay, and we know that sine is affiliated with the y-coordinate. If you look at your angles on the unit circle, none of these guys have a y-coordinate of 2/5. Okay, we've already said that 2/5 is a valid input to arcsine. So what that tells us is that this is some angle that is not on the unit circle. Okay, this is a defined expression. We're going to be able to work with this angle. There is such an angle. It's just not one that is on the unit circle. Okay, so at this point, you're going to want to draw a right triangle for it. Okay, so I will do that. Let's see. I guess I will do it up here. Okay, so here we go. We're going to draw our x-axis and our y-axis. Okay, and we need to leave some room in quadrants 1 and 4. Okay, so like I said, what do we know about this angle theta? We know that its sine is 2/5. Okay, that is a positive sine value. Sine is positive in quadrant 1. It is negative in quadrant 4. So we need to be drawing our angle in quadrant 1. Okay, so here we go. We've got this quadrant 1 angle. Okay, this is going to be theta. Okay, we're going to make a right triangle like this. Whoops. All right, so here we go. Draw down to the x-axis. There's your right triangle. Okay, we know that the sine of theta is equal to 2/5. Okay, sine is equal to the opposite over the hypotenuse, so this is going to allow us to label the sides. If we go straight across from theta, this is the opposite side. If we go across from the right angle, we know that's the hypotenuse. The other side is the adjacent side. And so since the opposite side, since the fraction is positive, we can just go ahead and equate the numerator and the denominator. So the opposite side needs to be labeled with a 2, the hypotenuse needs to be labeled with a 5, and we can use the Pythagorean theorem to come up with the adjacent side. Okay, so c squared is equal to a squared plus b squared. And so I know the hypotenuse is 5, so plug that in. 5 squared has to be equal to a squared plus 2 squared. So I'm going to get 25 is equal to a squared plus 4. Subtract 4 from both sides. You're going to get that a squared is equal to 21. And so this is going to tell us that a is the square root of 21. We need the positive version of the adjacent side because we are in quadrant 1. Okay, the adjacent side lies along the positive x-axis. Okay, so this is going to be labeled as the square root of 21. Okay, and so now where do we go from here? Okay, we do not know a measure of theta. Okay, we don't know, how many radians or how many degrees this angle is. We have, however, drawn a right triangle for it. Okay, so that is going to help us out. Okay, at this point, I am going to make a partition. Okay, we are going to go back to the original problem. Okay, and then incorporate the work we've already done. Okay, so let me just draw this out so our work does not get mixed up with the future work here. All right, just give me one more minute. And we will proceed. Okay, so I'm going to go back to the original problem here. I am going to write it down. Okay, we started with the tangent of 2 times the arcsine of 2/5. Okay, so if I write this, rewrite it, okay, this yellow 2 that I've highlighted, okay, has to stay there. Okay, but then arcsine of 2/5, we called that theta. Okay, so this whole thing is going to turn into the tangent of 2 theta. And look at that. We have a double angle formula. Yay! Okay, so we need to go back and dig up the double angle formulas for tangent. Okay, so if you go back, that was section 7.4. There is only one double angle formula for tangent. Remember, there's 3 different ones for the half angle. Okay, but for double angle, there's just one. I'm going to write it in red out to the side. We are told that the tangent of 2 times a is equal to 2 tangent of a over 1 minus tangent squared of a. Okay, so that's the identity. We have to go back and dig up this double angle formula, and now we have to apply it. So we can use it here. Okay, the only difference between the actual identity and what we have is that we're using theta instead of a. Okay, so I'm going to translate this into theta language. This is going to be 2 times the tangent of theta over 1 minus tangent squared of theta. Okay, so what do we do now? Well, we need to plug in for the tangent of theta. Okay, that's what you see in the numerator. The bottom has a tangent theta. That quantity is just squared. Okay, well, this is where the right triangle comes in. We have drawn a right triangle for theta, so we can read the tangent of theta from the triangle. The tangent is just the opposite over the adjacent. So that is going to be 2 over the square root of 21. Okay, that is going to be the tangent value here. Okay, so if you want to, you can just proceed, since we're going to still be doing some more calculation. So you can just save rationalizing for the final answer. Okay, you don't have to rationalize at this point. Just make sure you've got the opposite over the adjacent here, 2 over the square root of 21. Okay, that's what we're going to plug in for the tangent of theta. Let me write that out to the side. Again, the tangent of theta is 2 over the square root of 21, and I'll rationalize in the end. Okay, so this is going to be 2 times 2 over the square root of 21. The bottom is going to be 1 minus the tangent of theta. So the tangent of theta is 2 over the square root of 21. Okay, and we need to square that quantity. Okay, don't let this page number here get in your way. Okay, so scratch that out. So now we just need to simplify this. This is just a number. Okay, once we simplify it, we will have our answer. In the numerator, this is going to be 2 over 1 times 2 over the square root of 21. In the bottom, we've got 1 minus, we're squaring a fraction, so square the top to get 4, square the bottom to get 21, and then we just keep working. So in the numerator now, multiply across the top and across the bottom, we're going to get 4 over the square root of 21. In the denominator, we need to subtract the two fractions, so we need a common denominator. Since the 1 is really over 1, okay, the common denominator here is going to be 21. So for the left fraction, I need to multiply the bottom by 21 to get the correct denominator. Since I do it to the bottom, I need to do it to the top. And so we're going to get that 1 is equivalent to 21 over 21, which is right. And we're subtracting 4 over 21. Okay, so keep going. This is going to be, let's see, running out of room here. So this is going to be 4 over the square root of 21 over, if we combine the fractions into 1, we'll get a denominator of 21. Go across the top, 21 minus 4 is going to give us 17. Okay, and now just divide the fractions. So 4 over the square root of 21 times 21 over 17. All right, so almost there. We're going to get 4 times 21 over 17 times the square root of 21. Okay, we have to rationalize the denominator here. Okay, so this is getting a little crazy, running out of room. Okay, so this is going to give us 4 times 21 times the square root of 21 in the top. The bottom is going to be 17 times 21. Okay, so this 21 will cancel with this 21. Okay, and so the final answer here is going to be 4 times the square root of 21 over 17. Final answer. Okay, so that is what this quantity that we started with is equal to. Okay, you know, this was a strange problem, strange answer. This one doesn't have any weird calculator keystrokes. Like I said, if you're dealing with secant inverse or cotangent inverse, or well, let's see, cosecant, secant, cotangent inverse, those guys on the calculator can be a bit tricky. I can go ahead and check myself on the calculator because there's nothing weird about this one. So let me make sure you're in radians here. Okay, so I am going to do, let's do tangent of 2 times the arc sine of 2/5. Okay, make sure you're in radians, like I said. Okay, here's the decimal expansion. So now we need to check our answer. We got 4 square root of 21 over 17. We hopefully have a match. Whoops. So divide this by 17. And we do. So we know that we are correct for having found the exact value of tangent of 2 times the arc sine of 2/5.